Hey, welcome to another fabulous day of Calc 3 with tangent planes, normal lines, and differentials. Whoa, this section is jam-packed of stuff, and it's really cool. So you'll really see some fun stuff here, I think. Okay, so what do we know so far? Let's do a quick recap. We have represented surfaces in space by equations of this form right here. Little z is equal to little f parentheses x comma y. And this is known as explicit form. It's where the z is on one side and the x's and y's and stuff are on the other. And it's great, and it works. Well, we're going to look at a more general representation today, and this is sort of the key for this section. Okay, I really want to stress this because sometimes students, yeah, whatever, and they just don't get that the underlying foundation for this section is we're going to represent surfaces by having all the x's, y's, and z's on one side of the equation, to just move them over there if you need to, and then a zero on the other side. That's what's considered a more general representation of a surface in space. Okay, it's a surface in space, and it's somebody's level surface. You know how we, when we're finding level surfaces, we set a function of 3 variables to a constant. Well, imagine that you said, yeah, set it to a constant and have the constant be 0. So there you go. This is a level surface for the function of 3 variables. All right, and it is a surface. Now, let's say you're given an equation in explicit form. So z equals little f. What you need to do before you do anything from this section is you need to move the z to the other side so you could get a 0 on both sides of the equation. So it's real easy to do this. You just subtract z from both sides of the equation, okay? And you get 0 is equal to, whatever the x's and y's and junk was, minus z. And then this is who you're going to rename. Well, what are you going to rename him to? You're going to rename him to big F. So your big F is essentially little f xy minus z. And then you're setting that equal to 0. And that's the more general representation for a surface in space. So we can consider this surface to be a level surface for big F. Big F. So let's say you're given this general representation for a surface in space, f x y z equals 0, for this function. What are those level surfaces looking like? Well, just set this function equal to 0 to find that particular level surface. And I'm going to rearrange this a little bit by adding 4 to both sides of the equation. And does anybody recognize this equation to be something that we've studied in the past?
It's forming some kind of a
No.
circle.
Yeah,
or
it's a
3D
sphere.
parabola.
It's something in 3D. So
It's a sphere.
It's a sphere. Yep. Of radius 2 centered at the origin. There you go. That's the level surface. And we all know that a sphere is a lovely, lovely surface. It's always pretty. Yep. Okay. So now we're done with that example. Fine. Okay. Now let's move on. Let's talk about a tangent line to a surface. So if you got a point P on your surface, so it's 3D, so it's got 3 coordinates there, order triple, and you don't want your big F to have any weird partials. So let's say all the big F's partials are non-zero. Then a tangent line to your surface at that point is a tangent line to any curve which lies on that surface and contains the point. Okay, so I'm going to try drawing some stuff in 3D now. Let's not be too scared. So let me just draw sort of a capping surface because those are kind of fun. So let's say that this surface I just drew corresponds to this more general representation, big F x, y, z equals 0. And so this surface, there you go, like that. Okay. Now I'm going to pick a point on my surface. Okay, I don't know, right there. There's my point P, or P naught. Okay, now what? Well, let me draw a curve on the surface, but that passes through my point. Okay, here's a curve on the surface passing through the point. We'll call it big C. Then the curve, because it is a curve, you can represent it with some parametric equations. So you know parametric equations, right? Let's just call x is, say, some function of t, x of t, y is y of t, and z is z of t. And you can also rewrite the curve as a vector valued function by just simply taking the parametric equations and putting them in as the components for your vector valued function. That's equivalent. It's another way to represent the curve. All right, now here's the cool part. I'm going to need all of your knowledge from these past couple weeks. Since this curve lies on my surface S, it has to satisfy this function. What does that mean? Well, that means if I plug in x of t for x, y of t for the y, and z of t for z, it still better satisfy this equation. It still must be true. Why? Because the curve is sitting on the surface. So it's got to satisfy the surface's equation. Otherwise, we're in trouble. Now, here's the fun part. I think it's exciting. If big F is differentiable and the vector valued functions derivatives all exist, by the chain rule for a function of a single variable, big F prime of t, which you can also write df dt, is equal to, and so if you want, I can draw a tree for it. So your tree would look like this. Here's F. He's a function of x, y, and z. But x, y, and z are getting driven by the driver of the bus, and that's t. Okay? So you know your chain rule says df dt, and it's straight stem because t is a single independent variable. It's the partial of f with respect to x times dx dt plus the partial of f with respect to y, times dy dt plus the partial of f with respect to z times dz dt. And that has to equal the derivative of the right-hand side with respect to 0. And the right-hand side of that equation is 0, and the derivative of 0 is still going to be 0. Aha! So what? Well, here's the cool beans part. Doesn't this big old chain rule look like the dot product of two vectors? Because it's got that flavor, something times something, plus something times something, plus something times something. Doesn't it look like a dot product to you?
I recognize that.
Yeah, that's a dot product. It's got that whole flavor. So it's a dot product of who and who. Well, it's a dot product of del big F, the gradient for big F, and r prime t, the vector valued function's tangent vector. So that implies that the gradient of big F at this point P naught is orthogonal to every tangent vector of every curve on S going through the point P naught. That's got to be true. We'll let that soak in for a minute. I'm not sure if you really grasp the full impact of that. What does it look like visually? So if I go back to my picture here, what am I saying? If I draw a little tangent vector to this curve, I should probably use a different color. How about red? Tangent vector, there's r prime, and the gradient, big del F, is going to be orthogonal to that. What if I draw a different curve on the surface passing through the point P naught? So I have a different tangent vector, but del F is still going to be pointing straight up. And so I can get a whole collection of curves and a whole collection of tangent vectors. And I claim that the tangent vectors lie in the same plane, and del F is sort of orthogonal to that bed of tangent vectors, always. So all the tangent lines at P naught lie in a plane that is normal, orthogonal, to the gradient of big F. Now remember, the gradient of big F, which we denote del big F, is a vector that contains the first partials of big F. and at the point P naught. Finish off that. I should have left myself some more blank. So now we're going to define the meat and potatoes for this section. Here's the meat and potatoes, the main course. Tangent plane and normal lines. That's what you'll be asked to give on the homeworks and everything for this section. So here it is. Let big F be differentiable at some point P naught with the coordinates x naught, y naught, z naught on a surface S. And your surface S is given by this more general representation where everything's on one side and zero is on the other. It's like a level surface general representation, such that the gradient, big del F, isn't the zero vector. Then the plane through the point P naught that's normal to del F is called the tangent plane to S, that's the surface, at the point P naught. So visually, what does that look like? This tangent plane to your surface S at the point P naught. Well, let's look at what's going on here. Let's say you had some surface. I'll make it easy, like a capping surface. Here's some capping surface. And it's given by that equation, big F x, y, z equals 0. There's your surface. Okay, fine. We're going to pick a point on the surface. Okay, I don't know. How about over here? There's your P naught. Okay. What we're doing here is we're going to create a plane that's tangent to that point. And it turns out it's tangent to the surface also. And so this is a picture of your tangent plane. And what is that analogous to? In Calc 1, I hope you recall, one of the big things that you did over and over in Calc 1 is somebody gave you some curve, say, here's the graph of y equals f of x, and they picked a point here, P. Didn't they a lot of times say, give the equation of the tangent line to the curve? They did, a lot. Oh yeah, and they made you go get the derivative to get the slope. So all we're doing here is instead of a curve, we're looking at a surface here in space, and we're picking a point where there's a tangent plane to that point. Tangent plane instead of a tangent line. Pretty cool, huh? So why is that cool? Well, we're going to use the gradient as a normal vector to the tangent plane. And to get the plane equation, and this is from a few weeks back, you need a point on the plane and you need a vector normal to the plane in order to come up with that full equation. So that's important. And then also, what about the line that's normal to the, back here, here's your capping surface again. Here's your point P. What if I want to just get a line that's piercing the surface at that point? So this big old line here, or we call this the normal line, is puncturing the surface and it's orthogonal to the surface. That line is called the normal line to the surface S at the point P naught. Okay. So now we'll do some fun problems with that. So the GPA, the general person's agreement, will be from now on, just assume your del big F isn't the zero vector until later this week, because otherwise you'll not be able to get a nice tangent plane. Okay, so let's find an equation for the tangent plane. So let's do a quick review. This is from a few weeks ago. Remember the equation for a plane? If you have a point on the plane and a normal vector n with components a, b, c, the standard equation for a plane looks like this. Although some of you never use my standard equation on your homework because you keep hitting that view and example button. I like to see this as step 1. So I hope you remember that. And if you multiply it all out, then you get the more general equation. So if you've got some point on your tangent plane and somebody gives you the point on the surface that they want the tangent plane to the surface at, and you are able to find the big old gradient, this gradient is who you use as your normal vector to the plane. So this gradient is essentially serving the role of n here. They're one and the same. That's going to be your key. So here's the theorem to get your equation of a tangent plane. You got big F, it's differentiable at a point P naught. And keep in mind, big F is a function of 3 variables with everything on one side and 0 on the other. Then the equation of the tangent plane is the first component of your gradient evaluated at x naught, y naught, z naught. That's going to be some number times x minus the x coordinate of your point, plus the first partial of big F with respect to y evaluated at your point, times y minus y naught, plus the big partial with respect to z evaluated at your point. And that's, oops, multiplied by the quantity z minus z naught. That whole mess is equal to 0. And then you can multiply it all out. Now, a common student pitfall, common student mistake, and this is not just a silly mistake, this is somebody who's just not getting it. These fx, fy, and fz, those have to be pure numbers. In other words, you actually have to first find fx, fy, and fz, and then substitute the coordinates of the point so that these are numbers, because you want all of these to be numbers when you finally use them in your tangent plane equation. I don't want to see like x squareds and all that in a tangent plane equation, because then you miss the boat. A tangent plane, like any plane, the x, y, and z variables that you see in a tangent plane equation are always raised to the 1 power, because it's a linear. Okay, and then let's talk about the parametric equations of that normal line to the surface. This is that line that's piercing the surface at the point. And it's really easy because you're going to use the gradient at that point for the direction vector, because it is the direction vector. So your parametric equations are going to be super easy to get. You've got the coordinates of your point, x naught, y naught, z naught, and then your direction vector, those direction numbers are simply going to be the gradients components evaluated at the point, multiplied by t, of course. Those are the parametric equations. And again, these better be pure numbers, because you've plugged in the point at which you're finding this normal line. If I see x's and squareds and z's and blah, 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 multiplying with your parameter t, I'm going to go, uh-oh. Okay. Here we go. Okay, so I want you to notice that the next 2 examples I'm going to do something similar for both examples, and that is both examples have an equation that represents a surface in space, and we got to go get the equation of a tangent plane at a point and the parametric equations for a normal line to a point. Fine. But the 2 surface equations look very different. So I just want to point that out first so that you can see a little bit of what's going on here. Because when I give exams and quizzes on this material, I will try to fake you out and give one or the other or both to see if you get the distinction. What do I mean? Well, check out example 2. Do you notice that this equation is a big hot mess? And it doesn't look like z equals an f of xy. So this is an implicit function of x and y, because it doesn't have z on one side of the equation and all the rest of the junk on the other. Fine. And you already know about implicit functions because we talked about how to find the partials of z with respect to x and y. If you have an implicit function, you have to use those special formulas. Now, the next example we'll do after that example 2, you'll notice here a very different look. This is explicit. This is an explicit function of x and y. Very different flavor, okay? And I want you to notice how we have different approaches to these 2 different equations, but both of them represent surfaces in space, okay? It's not like they don't. And just to prove it to you, looking at example 2 here, I'm going to whip out my lovely graphing software because I can. And here, if I graph, what am I going to graph here? X squared Z cubed. Oh, was that a Y cubed? Ah, crap. Sorry, Y cubed. My bad. I gotta read this. Plus 2xz cubed equals 4 plus y squared z. I have no idea. What the heck does this look like? Oh my God, that's nuts. Oh, that's kind of pretty. Love it. Okay, so there's a surface in space. Nice, huh? Huge. Okay. So what are we doing? Well, they're picking a point somewhere on this surface, you know, like say right there. Stop spinning. You're killing me. You know, let's say they just picked a point right there, and we're going to have a tangent plane at that point, you know? Yay. And then what? Well, after we get done coming up with the equation of a tangent plane at that point, then if you can think of a normal line, you know, a line that's orthogonal to the surface at that point, you know, piercing through the surface, we'll find the parametric equations for that normal line. Pretty cool, huh? Are you guys excited, or maybe you don't care? Now, what about the next example? Well, the next example has fxy, but you can just replace fxy with z because that's essentially what it is. In fact, you'll want to do that before you'll see that'll be step one when we do that problem. And if I graph that guy's equation, what do I have here? Oh, it's out of range. I know what's going on here. Oh, thank you. I did that whole thing without recording. Oh, thanks for telling me. Okay, so the surface here is a really cool surface with, and I guess I should maybe graph it again, but I won't. Okay, so that's going to be some weird surface, and we saw that that surface kind of looked, you know, maybe something like that, and it was kind of all over the map. And we're going to find a normal vector to this surface. How do you find a normal vector? You're just going to get the gradient. So first, let's get the gradient. Oh wait, first of all, I need to do step one. My bad. Step one, and I better see this on your paper, you need fxyz equals 0. If I don't see that on your paper, you're going to lose a lot of points. I need to see that. Well, what do you mean? I want you to move everything to one side and 0 on the other. So you get that general representation that you need before you find the gradient. Now, does it matter which side of the equal sign that you get everything and which side the 0? Nah, not now. Okay, you can just pick a side that you like, and trust me, it'll still all come out to be the same answer. So I'm just going to move everything to the left. We already have a couple terms on the left. Okay, everybody with me? And then this junk on the left, we're going to rename it Big F. That's Big F. That's him. That's the guy. So you're going to get his gradient, which is just a vector that contains the first partials. And that is essentially a normal vector to any point x, y, z. And then we'll just plug in the coordinates for our point. So first we got to find del f, the gradient. All right, so let's see here. The partial with respect to x. Okay, the first term is going to give me 2xy cubed plus 2z cubed. And I think that's it for the first partial with respect to x, comma. Now let's take the partial with respect to y. First term, 3x squared y squared. Next term, 0. And then the last term, minus 2yz, comma. And then let's take the partial with respect to z. First term goes to 0. Second term is 6xz squared minus y squared. Okay, that is pretty hellacious. And now we're going to evaluate this at the point -1, 1, -1. And you know, you'll just substitute. I'm just going to put substitute everything. I do want to see that stuff on your paper, though, when you do handwritten work. Otherwise, I dock your points. I'm in a hurry right now. So I'm just going to get to it. I get -4, 5, and -7. And that is the answer for part A. That's a normal vector to the surface. It's a vector that's sticking out of the surface, if you will. Sticking right out. And we're going to use this vector to help us do the next two parts. It's going to be very useful. So we're going to find an equation in general form for the tangent plane to the surface at this same point. Great. We have all the ingredients. This right here is a normal vector to the plane. So you already got them. And you already got the point on the plane. So now you already know everything about plane equations from the last couple months. You just use all that and put it all together. So the first component, -4, x minus a -1, so that's the x coordinate of the first point, plus next component is 5, parentheses y minus the next coordinate of our point, 1, plus -7 times z minus a -1, that whole mess is equal to 0. And then you'll want to distribute and do some arithmetic in order to get general form. So I get -4x minus 4 plus 5y minus 5 minus 7z minus 7 equals 0. And then when I rearrange it, -4x plus 5y minus 7z equals 16. And we're done. And that's the answer for part B. That's a tangent plane to the surface. Yay! Success! Now let's get parametric equations for the normal line. We're almost done. Parametric equations, we got the direction vector. What's the direction vector? The gradient. It's sticking in the same direction as the normal vector, or as the normal line is. And so, and you got the point, -1, 1, -1. So let me just write those first, -1, 1, -1. And then here we're going to have -4t plus 5t and -7t. And boom, those are the parametric equations for a normal line. Done. Letter D, find del F to the level surface given by fxyz equals 0. We already did it. We already got that gradient. What do you mean? We got that del F was equal to, and I want to write it all out again, but this guy right here, without the x's, y's, and z's plugged in. So go see above. So we did this already. All right. And then finally, what's the level surface fxyz equals c if for the constant c if you were at the point 3, 2, 1? Well, if you look at big F up here, where we got everything on one side and 0 on the other, just plug in the point 3, 2, 1 and then set it equal to c. So you're going to have 3 squared 2 cubed plus 2 times 3 times 1 cubed minus 4 minus 2 squared 1 equals some constant, and I get the constant is 72. So that would be some other level surface. Okay. That concludes this example. So what's the recap of this example? You were given a surface that's an implicit form because it's not given by z or fxy equals. And you get everything on one side and 0 on the other, and that's the general representation for a surface. Then you go get big del F, the big gradient for big F. And that gives you a vector that's normal to your surface at any point x, y, z. And if you have a particular point you're dealing with, like we did, the point -1, 1, -1, you get your normal vector, which is the gradient. Use it to get equations for your tangent plane and normal line parametric equations. Fine. Now let's do the same thing all over again with a new surface. Now there's some extra stuff I threw in here though. What I'd like to do is I'd like to bring in some of last section stuff, directional derivative stuff, as well as this section all at the same time to see what happens. It might confuse you, but I'm hoping if there is some confusion, we clear it all up by the end of this little example. There's a lot going on here. And this example you won't find in the book because I came up with it on my own from teaching this class for so many years and noticing the pitfalls that students kept falling into. So here's a surface, only it's given to you explicitly. And I think when we graphed it, we found it was a paraboloid facing downward. Fine. It's kind of a cool paraboloid. All right. So we're going to find del F. Now be careful because this little del F is the 2D gradient. How do I know? Just the notation of it. Get comfortable. So this little del F, which is going to be a vector that's 2D, that will contain the partials, and I get negative 4x for the first component and negative 2y for the second component. I'm done with part A. Done. There it is. Letter B. Use the gradient of little f to help you find the directional derivative. Remember, that's a slope for the function at this point, P, with coordinates 1, -2, in the direction of the point Q. Now remember, directional derivatives are found by taking a dot product of your gradient with a unit vector pointing you in the same direction where you want to find this slope. Well, they didn't give us a unit vector yet. We got to do it. So first we're going to form the vector PQ, terminal minus initial. And then we're going to, brackets, unitize it. Because you've got to have a unit vector anytime you're doing that directional derivative. You don't, no partial credit. Sorry, can't do it. So if we find the magnitude of PQ first, square root of 4 squared plus 6 squared. Square root of 52. Oh, well, we could play 52 pickup. And when I simplify that, it's 2 squared of 13. Fine. So then the unit vector in the direction that I want to find this slope is going to be negative 4, 6 divided by 2 squared 13. And after reducing to lowest terms, I get the vector with components negative 2 over square root of 13, comma, 3 over square root of 13. Okay, fine. Now, you're going to evaluate the gradient at, well, first, we already found the gradient. It's up here. But we're going to evaluate him at the point P, 1, -2. So substituting in those coordinates for point P, 1, -2, I get my gradient has components -4 and +4. Okay, so now, oh boy, I did not leave myself any room. The directional derivative at the point P, so I'm going to just say f of P, is going to be the gradient -4, 4 dot product with the little unit vector pointing in the direction that we want to get this directional derivative. It's a slope. So now when I do the dot product, do the arithmetic here. Oh, that's going to be gross. I get 8 over square root of 13 plus 12 over square root of 13. And my final answer is 20 over square root of 13. Boom. And there you have it. That's the answer to letter B. Took us all that just to get the answer to letter B. And it's the directional derivative. Okay, now we're going to take a little different turn in the same problem. Letter C. Be careful here. We're going to find a normal vector to the surface. And keep in mind, this has to be a 3D vector. So you can't use the gradient little f, little del f. That's not going to cut it. And yet students do that to me. They go, here you go, here's a normal vector. And I go, thanks. And minus 10 points. Sorry. That's just a 2D vector that lies in the 2D XY plane. I want a vector that's punching out of the surface. So what you're going to have to do is step 1 is you're going to need to get your original functions equation written in this more general representation to start. Then the normal vector is going to be del big F, which is going to be a 3D vector containing the partials of big F. So that's how we're going to roll for letter C. So if you look at this explicit function of x and y they gave us, how do you rewrite it? You first cross out z, the fxy rather, and you replace that with the letter z. So do that first. And then get everything on one side and 0 on the other. Well, which side? It doesn't matter as long as you pick a side. Now, since z is the only guy on the right, it'll be easier for me to simply subtract z from both sides of the equation. That's the easy way to go. And there, I have everything on one side and 0 on the other. Yay! And you have to do step 1 for letter C. So step 1, I have 16 minus 2x squared minus y squared minus z equals 0. And all this junk that's on the left-hand side here, I'm renaming that big F. And it is a function of 3 variables there. You see, there's an x, there's x's, y's, and z. Yep. So now I can go get the gradient of big F. That's big del F. So let's go ahead and get those partials. I get a negative 4x, negative 2y, and negative 1. And then to wrap up letter C, you simply evaluate it at the point given with coordinates 1, negative 2, 10. So del F, big del F that is, evaluated at 1, negative 2, 10, you know, substitution, negative 4 times 1, comma, negative 2 times negative 2, comma, negative 1. So I get the letter C, the final answer for letter C is this vector, negative 4, positive 4, negative 1. So that's the answer for letter C. So what is that? That's a normal vector to the surface. It's a vector. So if your surface, you know, I don't know what, this was the paraboloid. You know, here's your paraboloid. So at the point with coordinates 1, negative 2, 10, you know, I don't know, I'm just guessing that would be like, let's say it was over here. This vector is punching straight out of the surface, making a 90-degree angle. That's all. And why do we care about that? Because see, that del F, del big F, is going to be a vector that's normal to the tangent plane here. So if I just graph the tangent plane, that's sticking out. So we're going to be able to do letters E and F really fast right now. Now that we got the big del F, we're going to use it. So for this problem now, let's go, I'll do letter D. I'll leave letter D for the moment. We'll get it in a second. Let's do letter E. Let's do equation of tangent plane. Because we can. We got what we need. So from our part C, we got negative 4x minus the x coordinate of the point, plus positive 4, y minus a minus 2, that's y plus 2, plus negative 1, z minus 10, that equals 0. And then after doing some distributing, and rearranging, and I also multiply both sides by a negative 1 if I have too many negatives. So once I rearrange everything, I've got negative 4x plus 4y minus z equals negative 22. That is correct. There's nothing wrong with that, except I don't like so many negatives because, you know, I like to stay positive. So I multiply both sides of the equation by negative 1 just to make more of the terms positive than negative. That's how I roll. So there's the equation of the tangent plane. 4x minus 4y plus z equals 22. Fantastic. And then letter F is super easy because they want parametric equations for the normal line to the surface, but we already have the direction vector at that point, 1, negative 2, 10. And so we can just use that as those numbers as the direction numbers for our line, our normal line. Cool. So the parametric equations are 1 minus 4t, -2 plus 4t, 10 minus t. There we have the parametric equations for the normal line. Fantastic. And then I'll back up to letter D where we have to describe level surfaces. So you know, level curves. Level curves are set fxy equal to a constant. So 16 minus 2x squared minus y squared equals a constant. If I rearrange this equation, it's going to actually be ellipses again. Oh, there's those ellipses. Those are level curves. So what are we guaranteed? The little del f will be orthogonal to these level curves. Big del f is orthogonal to the big old surface. So now the $64,000 question, letter G. This is the part that students just don't know because they're confused. And, you know, right now you might be confused because we're trying to learn a lot. Which vector, little del f, the big del f that you found in part C, which one of those gradients would give you direction of the maximum rate of increase on the surface at the point 1, -2, 10?
The gradient.
Well, both of these are gradients. One of them is the gradient of little f, that's a 2D vector. And the other one is the gradient of big F, and he's a 3D gradient.
Oh, so the 3D gradient is the plane.
Well, the 3D gradient is punching out of the surface. It's a normal vector to the surface. So if you had, you know, like let's say your capping surface, here's your point. This big del
I
F
see.
is pointing at that.
And the normal gradient is the
Little
2D
del
is
F
this on the XY
is
axis.
down here in the
Okay.
XY plane. Like little del F is, if you graphed him, he'd be somewhere here in the XY plane. He's a 2D vector. So which
All
one
right.
is pointing you in the direction of maximum rate of increase on the surface? This is a tough one, and I'm going to tell you the answer because I don't want to, you know, embarrass anybody. The answer is little del F. Well, that's a 2D vector, I know, but it's like a compass. And if you're here on the surface and you have a compass that's flat in your hand, it's pointing you in the direction of the maximum rate of increase. Big del F is a function that's pointing you, you know, off the planet. It's gonna, you know, if you strapped on a jetpack, you wanted to take off straight out of the earth, you know, you would go in the direction of big del F. So that wouldn't point you in the direction of the maximum rate of increase. So let's say you were a skier standing on the surface right here. Let's say here's you with your ski poles. Hey, hello. Which direction would you ski if you want, you know, let's say you were one of those hot dog skiers and you love steep slopes. You know, you would actually look at what little del F was telling you to do. And you'd actually ski in the opposite direction if you wanted maximum steepness going downhill. You wouldn't want to take a jetpack and go in the direction of big del F, because then you would be skiing in the outer space. You'd be blowing off the planet. That is not the direction they want to go if you were a skier. Well, maybe it is. I don't know. Hey, I like that kind of skiing where I ski straight up into the sky. Woohoo! Fun times, man. Good times. Good times. Yeah, but come on, you know, that's not going to happen. All right. New topic, angle of inclination. So we want to know, once you get your tangent plane, how much of an angle is it making with the horizontal, essentially. And that's kind of interesting to know. So here's a nice little diagram here. So let's say the green here is a tangent plane to some surface. You know, what kind of angle theta is it making with, you know, flat? And so we're going to use something that we did maybe a month ago. If you were finding the angle between two planes, do you remember this? You found the normal vector to one plane, call it n1. You found the normal vector to the other plane, n2, and cos of the angle between the two planes is the same as the angle between the two vectors, the two normal vectors. Except you want to guarantee when you're doing the angle between two planes that you don't get this other angle on the back side. You want the acute angle. So to guarantee that you get the acute angle, you put absolute value bars on the numerator. Now, you don't do this every time. Please don't make a silly mistake. When I ask you to find the angle between two vectors, don't put absolute value there. This is only when you are finding the angle between two planes. So what are we doing here? Well, the angle of inclination of this tangent plane is going to be, we'll first get this normal vector, which is essentially del big F. And then the flat plane, you know, the XY plane, an obvious normal vector to the XY plane is k hat. So for us, we're going to basically have our cosine theta between the angle of inclination of our tangent plane be the absolute value of the dot product of your del big F with k hat and divide by the product of their magnitude, except k hat's magnitude is always a 1. Ooh, that's sweet. We don't even really have to bother with it. So if you just take the dot product of del big F with k hat and divide by the magnitude of big, that's supposed to be magnitude of big del F, sorry, magnitude of big del F, you'll have it. And so this blank here, because the vector k is orthogonal to the xy plane, we're going to use him. Okay. So let's do an example where we find the angle of inclination of a tangent plane to a surface. Okay. And we'll do the same for example 2 above. Okay. So remember example 2, this was the implicit function of x and y that we did. And we got everything on one side and 0 on the other. I don't want to do the whole problem all over again. But we did get, after we got everything on one side and 0 on the other, I think we got, well, what did we get? I think we got that the del F was this vector here. You can check me from example 2. You did it already. So cos theta is going to be the absolute value of the dot product of this big del F with k hat, but that's just the vector 0, 0, 1. Cool. And divide by the magnitude of the big old gradient. Okay. And so I get cos theta is equal to absolute value of -7 all over square root of, oh, man, I think that's 90. And so then your theta is going to be cos inverse of 7 over square root of 90. And I get approximately 42.45 degrees. And that's it. Just using some previous knowledge here in this section. Kind of cool. Okay, new topic. And we'll do one more example. Okay, and then we'll save differentials till later. Yeah. So I'm going to talk about little del F and big del F again. So if little f is differentiable and you have the gradient of the function of little del F is orthogonal to the level curves of F. What about big F? Well, if big F is differentiable, at a point. And big del F isn't the zero vector, then big del F is normal to the level surface, right here, normal to the level surface through the point P naught. So the key that I want you to get is little del F is a vector in the plane, whereas big del F is a vector in space. That's key. And we just saw in the previous example, this is the one that you use when you're going to find directional derivatives. Now let's do another really great use of gradients. I love this one. I love this one. So before I do this one, I want to remind you that this problem is very similar to a previous problem. So do you recall from a previous section? Do you remember finding parametric equations of a line of intersection of two planes? I did this in class. It's a classic problem. I'll draw a picture of what it was. So here's a plane. Oh, that's not very nice. Let's try again. Here's a plane. And let's say another plane and intersects with this plane. So here's another plane. And they intersect along, you can kind of think of it like the binding of a book. And so the parametric equations that you want to get the, this is right, this blue line is the line of intersection. So go get the parametric equations. So I don't know if you remember this, but let me walk us through this real quick because it's going to make sense before I do this other problem. The way to do it is you got the normal vector for one of the planes, call it N1. You got the normal vector for the other plane, call it N2, say. And it turned out the direction vector for the line of intersection was the cross product of these two vectors. So the direction vector for the line was given by N1 cross N2. Does anybody remember this? Maybe not. So what does that have to do with example 5? Everything. So we're going to find a set of parametric equations for a tangent line now to the curve of intersection for these two surfaces. And they're graphing these two surfaces. This first one is an ellipsoid. And so that's in my picture, it's sort of that yellow egg right here. And then the other surface that's intersecting the egg is a paraboloid. And that's the green one there. Okay, so where do they intersect? Well, when the paraboloid cuts into the egg, you can kind of think of the intersection sort of, you know, right where it cuts in. It might look like something of an ellipse, I guess. And so the curve of intersection, this is the curve of intersection. It's an ellipse. And we're not trying to find the equation of the curve of intersection. I don't care about that. I don't care. They're giving us a point that lives on the curve of intersection. It's right there. There's the point P with coordinates 0, 1, 3. And if I draw a tangent line to that point, there it is. There's the pink line that's a tangent line to that curve of intersection. What does that got to do with this problem here? Well, here's the claim. If you find the gradient to both of these surfaces, and it's going to turn out the cross product of the gradients is going to give you a direction vector for this line. What? Yeah. So here, I'll even use the colors. So for the green paraboloid, if you find his gradient vector at this point P, it's going to be a vector that's sort of punching out of the paraboloid and making a 90-degree angle, okay? If you find the gradient for the ellipsoid, I'll do that one in red because yellow won't show up. So the ellipsoid is going to have his own gradient. Let's say it's that at the point 0, 1, 3. it turns out if you take the cross product of these two vectors, you will get a vector that is parallel to this line of intersection, and that will be the direction vector for your line, and then we win. So the claim is that if we get everything on one side and 0 on the other, so we get this first equation written as fxyz equals 0, big F, and then we rewrite the other equation, the one for the paraboloid, where we get everything on one side and 0 on the other, we'll call it big G. Then del F at the point 0, 1, 3, cross product del G at the point 0, 1, 3 gives a direction vector for the line. And that's a big deal. And yes, this is going to be on a future quiz and exam. It's that important. Plus, we get to use cross product. Isn't that exciting? It's got a lot of elements in it. You have to know about gradients, you have to know about cross products, and you have to know about parametric equations for a line. Triple whammy. That's why I love it. Triple whammy. Okay. Let's go in slow motion. First, let's get step 1, where we get everything on one side and 0 on the other for the first surface, which is the egg, the ellipsoid. So let's go do that. So if I get x squared plus 2y squared plus 2z squared minus 20 equals 0. So this is a more general representation of the ellipsoid. And everything that's on the left, call that big F. And then we'll do the same thing for the paraboloid equation, get everything on one side and 0 on the other, and then call all this junk on the left big G. Now let's get the gradient for big F. And you know, it's just a vector that contains the first partial. It's not that hard. I get 2x, comma 4y, comma 4z. And if I evaluate this gradient at the point they gave us with coordinates 0, 1, 3, I'm just going to do some substitution. 2 times 0, 4 times 1, 4 times 3. I get the vector 0, 4, 12. Save that for later. Now let's get the other gradient for the paraboloid. So big del G is just going to be a vector with the partials for big G. And I get, what, 2x, comma 2y, comma 1. And if I evaluate del big G at the point with coordinates 0, 1, 3, I get the vector 0, 2, 1. Now I'm ready. I can take del F, 0, 1, 3, cross product del G, 0, 1, 3, which is equal to, what do I want to do? I want to cross product 0, 4, 12 with 0, 2, 1. And you know, to get full credit in my class, I want to see the determinant method. I want to see I hat, j hat, k hat in the first row, 0, 4, 12 in the second row, and 0, 2, 1 in the last row. And then, you know, these 2 by 2 determinants multiplied with I hat minus the 2 by 2 determinant times j hat plus the 2 by 2 determinant times k hat. And it looks like I get the vector negative 20, 0, 0. Okay, we're almost there, because now we have all the ingredients to get the parametric equations for the line. So now you just kind of put it all together and you have it. So what I mean? So you've got the direction vector. So your parametric equations are, and you know, 0, 1, 3 are the coordinates of the point, and the 0 won't even bother. So this one, negative 20t, and then since the direction vector has 0 as his other components, you don't even have to do anything else. And here are the parametric equations for the tangent line to the curve of intersection. So when we did it for the two planes, the curve of intersection wasn't really a curve, it was a straight line. But now when we intersect two surfaces that aren't planes, the curve is that ellipse, so the tangent line isn't a line of intersection. And that's pretty much it. Pretty cool. And we're done with that example.